Okay, now I would like to continue on this path from practical implementation. So energy was already something there. The other thing is, when we say we are losing energy for coding or transmitting is not our part of the game. But in the computing, where actually do we lose the energy? And there are different parts. I will explain you this. So what you see here is timing consumed for the coding activities. Timing relates also later to energy, but just let's learn what happens. And there is a portion for time for the random generator. So we have random coefficients. And because we have random coefficients, somebody has to give us these random numbers. They're not lying around, right? So you have to calculate them. How you calculate, I will show you later. And then we have some finite field calculations. All this inverse, multiplication, addition, subtraction. This is the actually coding, right? This is filling up the matrix. This is the calculation. And then there is some other stuff. So red means other, and green is the time for computing, and blue is generating random numbers. This was for a generation size of 8. It's always 100%, and then we increased the maximal symbol size, so the packet size. How big are the packets? And interestingly, there is some behavior, but we don't know why this takes so much here, and then a little bit larger, it doesn't take so much. This always has to do a little bit with the architecture of the platform. Later, it will be more stabilized. If we increase now the generation size to 16, you will see, oh, the computing kicks in now, and then more computing for larger generation size. But also, look at this. There's a 10% of the time we are throwing random numbers. And if you go up and up, you see now, oh, with a very large generation size, now the statistics are way better. You see in the beginning with small packet sizes, the time is still there because you don't have to calculate so much. But when the calculation takes over, then the amount of time you're needing for pulling out the numbers is going percentually down. Overall, the energy will go up. I hope that you understand this. So one more 256. This is more the biggest one. Now you see really there's a huge portion of getting the random numbers out of the system. And this is something where you start to improve your coder, right? You say, why do we need so much time here? Yeah. Compared to the coding here, it's a big portion. It may not be so energy demanding as coding, but it will take you time. You're losing time for this. So what can you do? This one was for big packets, right? Now, when we talk about 5G and low latency, all this control theory, they don't have the big packets, right? What happens if you have very small packets? So now only some bytes, right? So we start with generation size again, and now we look what happens, right? I just go up to 256. So what you see here, now most of the time is used for getting the random numbers. Because it's the same amount of time maybe as I had before. Percentage is more because now the computing does not take so much time. But you're losing a lot of time just in getting out the random numbers. I will tell something more about the random numbers. Another thing in the implementation part is, and there I only show you which trend this is going. I told you that in 2013, more or less, in the coding speed, we were better than Intel. And I told you there's something called multi-threading that we used a little bit, right? Multi-threading for KODO was just to split the task in the user space. You could calculate this and that. And now we had some work of a student who wanted to exploit multi-core. There's a saying of Herb Supper, the free lunch is over. What do they mean? There was a time when the CPU, we always increased the coding speed, right? So coding speed, the speed of the core, right? And now we are at 4 gigahertz, and everybody says, okay, that's enough. And what we are doing now is we don't increase the speed of the CPU, we make more of them, multi-core. You can buy an Adapteva core for under $100 with 64 cores, right? NVIDIA cards have a lot of these cores that you can use. Question is, can you really take your coding and split it over different cores? It's very hard for other codes, but for the network coding core, it was quite flexible, and there was one way of doing that. Simon Wunderlich made one paper about this, and here what you see is the energy consumption for network coding, for the KODO library on multiple cores. And what it shows you on the Raspberry Pi, which has 4 cores, we got a speed up by 10 in distributing it. So when you remember what we have seen in the table from 2013, the speed up when we used multi-threading, there was some percentage better, right? Now we have here a 10x, not 10%, 10 times better. So multi-threading is not the same as many-core or multi-core. The question is what really happens here. How can you be 10 times faster when you only have 4 times the core? That is, if you want to empty your room and move to a new place, and you stop the time you are doing it, and suddenly you have 4 people helping you, you would expect, okay, if I can cut it down by 4, that would be already great. So everybody does the same as I do. But what is the analogy if you move? Now you have 4 people, and it goes even not only 4 times, it goes 10 times faster. There must be something like a piano, right? Which you alone, you have a lot of problems to get the piano out of your room, right? And this has to do with the architecture. There are some caches, L1, L2, L3. If you use them in a nice way, so if the chunks that you want to put there have the right size, the whole thing becomes faster. And because the multi-threading, you have smaller pieces, you could use more efficiently these caches. So in other words, now the coding speed depends also on the platform, on the architecture. And therefore we are looking into so many different things to understand where the coding speed comes from. But just to show where's the tendency now? Where do we try to get more speed, more and more speed? And this is towards many-core. And the other codes, can they follow this many-core? Not so much. Some of the codes are very hard to parallelize. They have a given matrix, and you have to understand the dependency of the others. Because we have random, it's easier for us to spread it, just as an idea.